In this tutorial we discuss the alternating series test. This test provides conditions under which an alternating series converges. First we need to explain what an alternating series is. Consider for example the harmonic series. Here the underlying sequence is given by 1 over n for n greater or equal to 1. In particular the elements of this sequence are 1, a half, a third, a quarter and so forth. Note how each element in this sequence is positive, that means all have the same sign. Next we introduce a small but significant change to our series. Consider the series taken over -1 to the power n divided by n. Then this is the underlying sequence and its elements are -1 to the power 1 over 1, which is -1, -1 to the power 2 over 2, which is plus a half, -1 to the power 3 over 3, which is minus a third, -1 to the power 4 over 4, which is plus a quarter, and so on. Note how the first, third, and fifth element are all negative, whereas the second, fourth, and sixth element are all positive. Surely this pattern of an alternating sign continues in the sequence, since we alternatingly raise -1 to an odd or even integer, which either introduces a minus sign or not. This idea of an alternating sign in the underlying sequence is what defines an alternating series. More precisely, take a series where we sum over the sequence an. Such a series is called an alternating series if any two consecutive terms in the underlying sequence an have different signs. That means the sign in the underlying sequence alters between plus and minus. We already looked at the example of the series over the sequence -1 to the power n divided by n. This series is clearly alternating, as we can tell from the changing signs in the underlying sequence. Now if we consider the series over the sequence -1 to the power n plus 1 divided by n, then we realize that this series is also alternating. Note, however, how the role of the positive and negative terms is reversed this time. This happens because we raise -1 to the power n plus 1. Therefore the odd elements in our sequence are positive and the even elements are negative. All of the following series are also examples for alternating series. First we take the sum over -1 to the power n plus 1 times n over n plus 1. Next we take the sum over -2 to the power n times n factorial. Finally we take the sum over -1 divided by 100 to the power n minus 1. We don't even need to calculate the elements of the underlying sequences to see that the sign changes in consecutive terms. Consider the first series. Here the underlying sequence is -1 to the power n plus 1 times n over n plus 1. The part n over n plus 1 is always positive, but the part -1 to the power n plus 1 will change its sign every time we increase n by 1. And this is what causes the sign in our sequence to alter. Likewise in the second series, the part n factorial is positive and the sign alters because of the part -2 to the power n. In the third series again, we have a strictly positive part and a part which alters the sign. Therefore, the series is alternating. Next we want to investigate under which conditions an alternating series converges. This test is called the alternating series test. So let us assume we have given an alternating series. That means consecutive terms in the underlying sequence an have different signs. Such a series converges if the following two properties are satisfied. Firstly, the absolute value of an is greater or equal than the absolute value of an plus 1. That means if we forget about any signs in the underlying sequence, then we have a decreasing sequence, where any given element of the sequence is small or equal than its predecessor. At least we want to see this behavior from a certain element onwards. The second property requires the absolute value of the underlying sequence to converge to 0. Overall, the alternating series test states that an alternating series converges if both properties 1 and 2 are satisfied. Let us use the alternating series test to study our examples. First we consider the series taken over -1 to the power n divided by n. Earlier we have established that this series is an alternating series. In order to decide whether it converges, we need to study its underlying sequence. Here the underlying sequence is an equal to -1 to the power n divided by n for n greater or equal to 1. Therefore, the absolute value of an is just 1 over n. We need to check our two conditions. First, we need to compare the absolute value of an with the absolute value of an plus 1. Now the absolute value of an equals 1 over n. Surely this is greater than 1 over n plus 1, which coincides with the absolute value of an plus 1. Hence, the first condition is satisfied. For the second condition, we need to study the limit of the absolute value of an. That means we study the limit of the sequence 1 over n. But this limit equals 0, and so the second condition is satisfied as well. Therefore, the alternating series test tells us that our given series converges. However, the alternating series test does not always work. For example, consider the following alternating series. Here the underlying sequence is an equal to minus 1 to the power n plus 1 times n over n plus 1, and so the absolute value of an equals n over n plus 1. Now if we just concentrate on the second property of the alternating series test, we need to study the limit of n over n plus 1 as n tends to infinity. But you can check that this limit turns out to be 1. Hence the limit of the absolute value of an is not 0, and so the second property of the alternating series test is violated. This means that we cannot apply the alternating series test. Nevertheless, one can conclude that this alternating series does not converge, for instance by use of the divergence test. Next, consider the following alternating series. Here the underlying sequence is an equal to minus 2 to the power n times n factorial, so the absolute value of an equals 2 to the power n times n factorial. Let us study the first condition of the alternating series test. We have that the absolute value of an equals 2 to the power n times n factorial. This is clearly less than 2 to the power n plus 1 times n plus 1 factorial, which turns out to be the absolute value of an plus 1. So overall we get that the absolute value of an is less than the absolute value of an plus 1. Hence the first property in the alternating series test is violated, and therefore the alternating series test cannot be applied. Nevertheless, one can argue using the ratio test, for instance, that the given series has no limit. Let us consider our final series. Here the underlying sequence is given by an equals minus 1 divided by 100 to the power n minus 1. Then the absolute value is 1 divided by 100 to the power n minus 1. Let us check the two conditions of the alternating series test. The absolute value an equals 1 over 100 to the power n minus 1. This is greater than 1 over 100 to the power n, which is the absolute value of an plus 1. Hence the first condition is satisfied. For the second condition, we study the limit of the absolute value of an, which is the limit of the sequence 1 over 100 to the power n minus 1. As this limit equals 0, the second condition is satisfied as well. Therefore, in this case, the alternating series test implies that this series converges.